So this exercise is related to thermal physics, and we did first 21 questions from this exercise. So question 22, I'll start with. This is question 22. A typical car has an internal volume of 2.5 meter cube. On a fine day, the sun heats the interior of a car from a temperature of 20 degrees centigrade to a temperature of 55. Calculate the number of the molecules of air that must escape from a car if the pressure remain constant. So if we want to keep pressure constant, we can use the general gas equation, and this is about the number of particles. So we have the equation PV is equals to nRT, and where n is a number of the moles, so we can say PV is equals to number of moles is number of like the mole equals to number of the particles divided by Avogadro's constant, which is Na RT. So and R over Na is what? R over Na is equals to the Boltzmann constant. So we can say PV is equals to NKT. So now the general gas equation can be modified as PV is equals to NKT. So you can use PV is equals to nRT, or you can directly use PV is equals to NKT. But we'll use PV is equals to NKT because this formula involves. So we want to determine how many particles should escape to keep the pressure constant. So we will have the formula PV is equals to NKT. So first we'll determine the number of the particles at 20, and then we'll determine the number of the particles at 55. And then we take a difference to know how many particles should escape. So PV is equals to KT is equals to N1. And if it is N1, the internal volume is there, which is given. The pressure does not change. As I mentioned, the pressure does not change. And K is there and T is the temperature. And same way, we will determine PV is equals to KT. We'll determine the number of the particles at 55. But remember one thing, the SI unit of a temperature is Kelvin. So you have to add 273. And to know how many particles should escape, so you have to work out delta N, the change in the number of the particles. So we have the pressure, which is 1 into 10 to the power 3, 101 into 10 to the power 3, sorry. So 101 into 10 to the power 3, we have the volume 2.5, and we have the Boltzmann constant, which is 1.38 into 10 to the power minus 23. That will be given, and add 273, so this will become 293. This will give us the value for N1, and value for N2 will be 101 into 10 to the power 3. The volume, again, it's the same 2.5. K is the constant, 1.38 into 10 to the power minus 23, and multiplied by temperature. So it will be 273 plus 55. So it will be 328. And then this will give us a value for N2. And then we'll just simply take a difference between the two group of particles at different temperatures, and that will give us how many particles will escape. State an assumption you made whenever we are solving such questions. What is our assumption? We assume that the gas will behave like it's an ideal gas. Always, because these gas equations are only applicable for ideal gas, so we consider that these gases are ideal gases, or a gas is ideal gas, and same type of particles are there. That is also another thing. According to the Football Association FA rules, the football used in a professional match should have a circumference of 68 centimeter to 70 centimeter. The pressure of air in the football must be between 60,000 Pascal to 1,100 sorry, 110 kilopascal above the atmosphere. A football is inflated with an air at 16. When inflated, the circumference of a ball is 68.5 and it contained 2.5 exponent 23 molecules. Deduce whether this football met the FA rules. Atmospheric pressure is 105 kilopascal. So simply what we can do, like first we can determine its radius, and from the radius we'll determine the volume, and a volume then we'll find the pressure. So first we'll determine the circumference of the football, and from the like we'll use the circumference to determine the radius. From radius we'll use it to find the volume, and then from volume we'll find uh, the excess pressure, like what is the excess pressure is there as in dimension. So the calculation for this one, the circumference is given 68 points. So circumference is equals to 2 pi r, which is 68 centimeters. So we have to convert into meters. So 0.685 to pi is 3.14, and we'll determine the radius. This whole will go there in division. So the radius will be 0.109 meter. That is the radius. From a radius, we'll determine its volume. The volume will be equals to 4 by 3 pi r cube, because sphere is there. So 4 into 3.14 into 0.109 cube divided by 3. That will give us a volume which is 5.42 into 10 to the power minus 3. That is the volume of the football. Then we use a formula PV is equals to NKT. So if I want to determine the pressure, it will be NKT divided by V, where N is the number of the particles, which is 2.5 into 10 to the power 23, 1.38 exponent minus 23 is a Boltzmann constant. We add 273. So 16 plus 273 divided by the volume which we calculated 4.2 into 10 to the power minus 3. This will give us a pressure which is 1.84 into 10 to the power 5 Pascal. Now, we need the resultant. So inside, when we calculated the pressure from inside, it is 1.84. And the pressure from outside is the 1.05. That is given in the question. So we want to determine the resultant pressure. So inside pressure, like outward pressure minus inward pressure will give us the resultant pressure. So this will be 1.84 into 10 to the power 5 minus the atmospheric pressure 1.05 into 10 to the power 5 will be there. That is the atmospheric pressure. So when we take a difference of these two, we'll get 7.9 into 10 to the power 4 Pascal, or 79,000 Pascal, or 79 kilopascal. And according to FA rules, so it must have a pressure. The pressure of air in the football must be between 60 kilopascal or 110 kilopascal above the atmosphere. Like that. So it is 79 kilopascal above the atmosphere or more than the atmosphere. So means this football is within the FA rules. The pressure in the football is within the FA rule. And the pressure inside the football decreases as the temperature inside volume of remain constant in terms of motion of particle. So this is explanation like, so as the temperature will increase, the particle move faster, there will be a greater change in momentum or more collisions. So rate of change of momentum, if a temperature decrease, rate of change of momentum will also decrease. So the pressure will also decrease. You have to relate the temperature with the speed, and then speed with the momentum, and momentum with the pressure here. So this was the thermal physics question. 22 and 23.